everyone. So let's continue the conversation on pKa and pKb for acids and bases. And in this example, we're told the trimethyl ammonium ion, which is a CH3,3NH+, is the conjugate acid of the weak base trimethyl amine, CH3N, right? So without the proton. So these are, of course, a conjugate acid-base pair. We're told a chemical handbook gives the pKa value of the trimethyl ammonium ion as 9.8. And then we're asked, what is the Kb value for trimethyl amine? All right, so let's just write this down a bit clearer for ourselves. So pKa is 9.8 naught for CH3,3NH+, right? And what we ultimately want to get to is we want to get the Kb of the base that gives this. So what is the relationship between the trimethyl ammonium ion and the weak base trimethyl amine? So if you think about it, CH3,3N when dissolved in aqueous solution can react with water, H2O, liquid, to form an equilibrium with this CH3,3N plus aqueous plus OH minus aqueous, right? And what we are interested in calculating is what is the Kb for this base, right, in water. And what we're given is the information about, let's do that in red. We're given the pKa, like I wrote down, for this conjugate acid. All right. So what can we do? Well, from the pKa of the acid, we can actually calculate the Ka for the conjugate acid, right? Because we know the relationship between Ka and pKa is this, right? Because why? pKa is equal to minus the log of the Ka. And if you solve that for Ka, then you get Ka is equal to 10 to the negative pKa. So that means if we plug in here 10 to the negative 9.8 naught, you will get a value of 1.584 and so on, 10 to the negative 10 Ka. And this is the Ka for the conjugate acid. All right. Now, to relate the conjugate acid to the conjugate base, we can recall that the auto-ionization constant for water is equal to the product between the ionization acid constant and that for the base. So that means we can just solve for the Kb and get Kw over Ka. And that is 1.0 times 10 to the negative 14 divided by this value we just calculated, which is rounded to 6.3 times 10 to the negative 5, right? Because just as with pH, we look at the numbers after the decimal. So 9.80, two significant figures. So that's the Kb for the conjugate, for the base of the conjugate acid. All right, and that's how you work it back. Different manner, alternative. So an alternative that that you can also remind yourself of is, of course, that the sum of pKa plus pKb must equal to 14.00. So that means that the pKb of our conjugate base, so in this case pKb of our base, right? So pKa of conjugate acid, pKb, is equal to 14.00 minus pKa. Alright, and we're given the pKa, so that's 14.00 minus the 9.80, and that's equal to 4.02. So then, once we have the pKb, so that's the pKb of the base, and then we can just calculate the Kb in the same manner, so that's equal to 10 to the negative pKb, because why? pKb is equal to negative the log of the Kb. So Kb is equal to 10 to the negative 4.20, and then that should also give you a value of 6.3 times 10 to the negative 5. Alright? So however you do it, as long as you remember that pKa and pKb, in this case, the reason why we can relate it is because it's for an acid-base conjugate pair, and that we can relate using the Ka and Kb value for using Kw, or we can use Ka and pKb using the 14, the sum of them giving 14. And the only reason we can do all of this is because they are different by one proton, because they are acid-base conjugate pairs, right? You can't just do it for any random acids and bases. That does not work. It's because they are conjugate pairs. All right. Thank you for watching. I'll see you in the next video.